So, well, it's 2:30, so I'm going to go ahead and start recording just in case no one shows up today. I'm not quite sure. So what I'm going to do is I'm going to do the questions that we had to do for work today, which were at chapter 17, section 2, talks about capacitors. Capacitors is a device that stores electrical potential energy. It actually turning the frequency of the radio receiver is a capacitor. Eliminating spark in an automobile ignition system is a capacitor. Stores energy in electric flashes. Those are also capacitors. So if we look at what we were doing today, is we're actually looking at how the capacitors work depending on the size and the shape of the capacitor. So, and then they gave us some units. So the main ones that you need to have is you need to know that F stands for Faraday, and that equals coulombs per unit of voltage. You also will need to know C equals Q divided by the change in V, which is the magnitude of the charge in a plate over potential difference. You also will need to know that C equals that epsilon, which is a funny looking E, O, and A over D. So what we're going to do is I'm going to go ahead and go into the practice problems. But before I do want to talk a couple of things I thought was important. When you're talking about material between a capacitor plate that can change the capacity is a dielectric. And what that is that's material between a parallel plate capacitor. Insulators known as air, rubber, glass, and wax paper would be in between there to help discharge a capacitor, to help with that. So let's look at question number 1 on page 595. So on 595, it says that it's a 4 UF capacitors connected to a 12 volt. What is the charge of each plate of the capacitor? So the first thing that I would like you to do is I would like you to draw a circuit. So if we're drawing a circuit, the first thing that you would need to know is this right here actually states for a battery. And then what we have is we have a capacitor. So we're going to do a circle and we're going to do a C. That's going to tell us it's a capacitor. So what happens is you have a positive and a negative on your battery. This right now is basically telling you there's 2 batteries. Circuits are going around, and this capacitor changes the amount of voltage there. So it says, what is the change on each place of the capacitor? So the first thing that you want to do is you will want to write down your variables. So my capacitor is 400 US. My change in voltage 1, well, it's a 12 volt battery. So that would be 12 volts. And then my voltage 2 is going to be 1.50. So you need to have all that first. So if you draw the diagram showing the capacitor, showing that you have a voltage of 12 voltage, and then as it goes through with the voltage 2, 1.5, which we're not really going to specify right now, but we could specify it later once we start drawing these type of circuits. So the first question is asking us about Q. So we're going to use Q equals C times the change in voltage 1. So if we look at C, we have these units of UF. And what we're going to do is we're going to change that to F instead. To be able to do that, we're going to move our decimal place over. So now our C equals 4.00 times 10 to the negative 6 Faraday. And we're going to multiply that by our voltage, which is 12 volts. So if you take your calculator, make sure that your mode is right, which mine is right this time. So what I'm going to do is I'm going to take 4.00 times 10 to the negative 6. And I'm going to multiply that by 12 volts. and I get 4.8 times 10 to the fifth. So your first answer is 4.8 times 10 to the negative fifth. But we're not done yet because there is a second part of this problem. It says that the same capacitor is connected to a 1.5 volt battery. How much electricity is potential energy stored?
Miss Long.
What I'm going to do here is now I have a 1.5 voltage battery. My capacitor stays the same, but it wants us to find out for number 2. For that, they're asking for our potential energy. Since we're doing potential energy is stored, we're going to do PE equals 1/2 times C times the change in voltage 2, and we're going to square it. Okay? So we're going to do, and I'm going to change that 1/2 to a decimal instead of a fraction. So that's 0.05. I'm going to times that by C, and remember, we change our C to Faraday's by itself and get rid of the U. So that is going to be 4.00 times 10 to the negative 6 Faraday. And we're going to multiply that by our voltage 2. So we're using 1.5 this time instead of 12 volts. So we're going to times it by 1.50 voltage. And this time we're going to square it because that's what the formula says for potential energy. So what we're going to do is we're going to do 0.05 times 4.00 times 10 caret negative 6. And we're going to multiply that by 1.50. Close our bracket. We're going to square that. And I got 4.5 times 10 to the negative 7.
Miss Long.
Yes, ma'am.
Is it 1/2 just 0.5 instead of 0.05?
I don't know. That is a really good question, Bailey.
4.5 times 10 to the negative 6.
Oh, girl, you are right. God bless me. Thank you, Bailey. I was getting ready to ask, does anybody have any questions? And Miss Bailey has fixed me already. So let me change that. Sorry, baby. I don't know how to do a decimal. Because half is 0.50, right? Yes, it is. Questions about number 1? Jordan, you good so far?
Yes, ma'am.
Okay, cool. Do I need to give you a minute or can I erase it?
All good.
Okay. You understand the drawing the circuit and everything? Everybody good with that too? Because I wanted you to go ahead and start doing that now, because starting tomorrow, we're going to start talking about drawing circuits, and I want to make sure you know how to do that, okay? So let's see if Miss Long can do number 2. All right, so number 2 says, the parallel plate capacitor has a charge of 6.0 coulombs when charged with potential difference between 1.25 volts. Find the capacitance. So for number 2, we have Q, which is equals 6.0 microcoulombs. Change in velocity 1, which is 1.25 volts. And that's all we've got so far, right? Yep, that's all we got so far. So what we have is we have a battery of 1.25 volts. And then we have another capacitor, right? And that capacitor is 6.0 MCs, or UC, excuse me. So what we're trying to find here is we're trying to find the answer in C. So we're trying to find C. That is equal to Q divided by the change in V1. So what we're going to do is we're going to change this again to 6.0 times 10 to the negative 6 coulombs. And we're going to divide that by our voltage, which is 1.25. If I take my calculator, alpha y inner, 6.00 times 10 caret negative 6 over 1.25. That's going to give us 4.8 times 10 to the negative 6. And that's going to be in Faradays because we're talking about potential energy. So for B, not potential energy, capacitance. How much electrical potential energy is stored when the capacitor is connected to a 1.5 voltage battery? So now we're looking for that. So it says it's a 1.50, right? Voltage battery? Yep, it does. And now we're trying to find potential energy. Remember, for potential energy, we're going to be P equals 1/2 times C, change in V2 squared, just like we did before. So I'm going to use 0.5 this time. 0.5. Ma'am? Are you good, Bailey?
Yes, ma'am, I'm good.
Okay, I'm sorry. 4.8 times 10 to the negative 6 Faradays. And then I'm going to take my 1.50 voltage squared. And so I'm basically doing the same thing as I did on the first problem, just with different numbers this time. So what I'm going to do is I'm going to do 0.5 times 4.8 times 10 caret negative 6, 1.50, close, and I'm going to square that. And I get 5.4 times 10 to the negative 6, and this is going to be in watt unit. Joules again, because we're doing kinetic energy. Is everybody good so far with question number 1 and question number 2? They were almost identical. Okay. Let's go to question number 3. Question number 3 says a capacitor has the capacity of 2.00 pF. What is potential energy would be required to store 18.0 PC. So the first thing we're going to do is our C equals 2.00 pF. Our Q equals 18.0 PC. And our change in voltage, nope, we ain't got change in voltage yet. So what we're going to do here is we're looking for the change in voltage of 1. To be able to do that, we're going to take Q and divide it by C. So my Q is 18.0 times 10 to the negative 12 coulombs. And then my C is 2.00 times 10 to the negative 12 Faradays. And I'm looking for voltage this time. So I do alpha Y inner. I do 18.0 times 10 caret negative 12 over 2.00 times 10 caret negative 12 over, and I got 9.
Miss Long, why do we change our thing to negative 12 instead of doing negative 6?
Because the units that we have, which is P, we want to get rid of P, and we want to go just for Faradays and just for coulombs.
Okay.
And that's all we're doing. The only thing we're doing is just changing our units and using these numbers. Why don't they just give us these numbers? I don't know. That is a pretty good question. So on this one, we have a 9 volt. We have a capacitor of 2.00 pF, or you can do your capacitor 2.0 times 10 to the negative 12. And that's all we have, and that's what you would draw for number 3. Now B is asking us again, but this time it's telling us that how much charge is stored when the potential energy difference is 2.5 volts. So instead of 9 volts, now it's 2.5 volts. So now we're looking for potential energy this time. So for this one, we're going to try to find Q. That's what we're missing. That is C times the change in our voltage 2. Use the same C we had, 2.00 times 10 to the negative 12 Faradays. And we're going to multiply that by our voltage this time. Our voltage is 2.5 volts. So in my calculator, I'm going to do 2.00 times 10 caret negative 12 times 2.5. And I get 5 times 10 to the negative 12. And that's going to be in coulombs, because we're talking about a charge. Questions so far? I know I'm kind of going fast, but I am videotaping it just in case. Okay, for D. On 4, it says you were asked to design a parallel plate capacitor that has a capacity of 1.0 Faraday and the plate separation is 1.00 millimeters. Calculate the required surface area of each plate. Is this a realistic size for a capacitor? So what we have, if we have the capacity is 1.00 Faraday. It tells us that the plate separation is 1 millimeter, right? So that is my displacement. And what it's asking us for is it's trying to find surface area. So we're going to use A equals CD over EO. So our C is 1.00 Faraday. We're going to multiply that by our D, which we're going to change that to 1.00 times 10 to the negative 3 meters. And we're going to divide that by our EO, which is 8.85 times 10 to the negative 12 C squared N squared. Now, where did I get the 8.5 from?
That was from the table, right?
Yes, it's from the table, and it should be something. I wrote it in my notes, and make sure that you have it in yours, because that will be something that you will need to know that number. Okay? So, doing that, alpha y enter, you're going to do 1.00 times 1.00 times 10 caret negative 3. And then we're going to divide that by 8.85 times 10 to the caret negative 12. And what am I getting? And I did scientific notation. Mine was 1.129943503 times 10 to the 8th, which I went and rounded it up to 1.13 times 10 to the 8th power. Now, is that realistic? The answer to that question is yes, it is realistic. I know I kind of went fast. I'm going to stop the video, and then I will open it up for y'all's questions, okay?